Hi everyone, we are very excited to be presenting the food recognition benchmark at the AI and nutrition track at AMLD this year. My name is Mohanty and I am the CEO and co-founder of AIcrowd. To talk about the problem, the whole challenge and the benchmark revolves around the MyFood project, which is a project at EPFL where the goal is to enable millions of people to track their food consumption by easy to use apps where they can simply take a picture and the app can eventually tell them the overall nutritional consumption over time. Now, the use of artificial intelligence to kind of look at a single image and predict the nutrition is still a very hard problem. So we are looking at one problem at a time. The problem we are looking at is if we have hundreds and thousands of daily real world images like these taken by real people, can we simply predict what are the food items that are in the image and what are their object boundaries? Because if we have a good understanding of what food items are in the images and where they are, then by adding layers of depth estimation, we can still come up with a rough estimation of what is the volume of each of the food items. And if we get both the problems right, then we are already pretty far away when it comes to estimating the nutritional content represented in a particular image. But this is still a hard problem. In this particular benchmark, we are releasing 39,000 real-world images collected by users of the particular app, and we have 273 food classes. Now, when you have these many food classes on a real-world data set, the class imbalance is also high, meaning that there are some food items which are represented way too much, and there's some food items where we barely have any images. And that makes the problem very hard and also interesting from a machine learning point of view, because if we manage to kind of solve it in a way that the overall time that is taken to annotate these images or to eventually predict the nutritional estimate from images, then we are already solving a really hard problem using AI. The way we approach this problem is by launching a large benchmark, the Food Recognition Challenge on AIcrowd, which is a platform in which you can crowdsource real-world problems where participants come in with solutions using AI. In this problem, over the last year, we ran 4 different rounds with 4 different versions of the problem. And the way this works is we release the training dataset in the beginning. Then participants, they train their AI models. Then they submit their model along with the code and the model base they submit to the platform. We version and evaluate these models. And how do we do that? By taking some images which the users have never seen before, and the users' models have never seen before, and using their models to make predictions on these private images. And then these images are used to kind of compare all the models that we have received through the whole competition. And then we take all these models and we deploy them as a simple API so that the MyFood project can use that API to add more efficiency to their annotation processes. What that enables is the increased efficiency in the MyFood project leads to more images which now feed back to the training dataset, which again goes back to the same cycle where participants get more training data to train their models, and then they submit their models again to the platform, we version and evaluate, and then we deploy in production. And by using this whole cycle, we hope that the overall time that is broadly taken to annotate these images is something that continuously keeps decreasing over time, and hopefully someday we will never actually need any human intervention to be able to annotate these images to reliably give reliable predictions. Now, the idea that you put up a training data set and a problem formulation and hundreds and thousands of people will come in to solve them is great in practice. But to get it to work, a lot of effort needs to go out. And the team at AIcrowd and our partners at MyFood and EPFL were always very motivated to make that happen. So to help participants and practitioners of AI to get started on this problem, we created exhaustive starter kits to help people get an understanding of this data set, to get an understanding of the baselines that we released. So instead of just asking, hey guys, we have a problem, can you just solve this problem with these predictive models, we train some baselines using state of the art methods, and we release these baselines along with the code for all the participants to tweak. Many participants come in and they build up on top of these baselines, or they come up with their completely different solutions. But this enables a healthy ecosystem where anyone who wants to come in and contribute to this problem can still get started without the high barrier to entry that is usually there for a lot of problems in AI. So many of the top participants that came up with great solutions a year ago, they were just using this project to just learn about AI. And now they are at the forefront of AI research when it comes to detecting food items across real-world dataset. Across the whole competition, we managed to get some really good submissions in total, and and today is actually the day when the fourth round of the competition ends, and we already have really high precisions and recalls in terms of these predictive models. I will show some demos on what these predictions look like in a bit. So what did the participation look like? Throughout the whole competition, we managed to attract 992 participants, that is over a course of 1 year. These 992 participants submitted 2,595 submissions, and each of them are models and codes. And if you take all these models and code, it's 2.5 terabytes of user submitted code and models which we have available on these problems, and all collected through this benchmark. And if you take some of the top models and try and use it on real world images which the models have never seen before, these are just some examples of the predictions which the models make. And now imagine how easy it would make it to be able to kind of scale the whole annotation process. If millions of users start submitting images of their daily food items, and we can figure out how to scale an annotation pipeline where by using these assistive models, we engage with a group of annotators where the overall time taken to annotate a single image keeps decreasing over time, just because all the annotators have to do is basically take this prediction and just correct the boundaries and map the correct class if at all it is kind of getting it wrong. And in the process, with increasing data sets, our models will only keep getting better. And now, without taking more time, I would open up the floor for some of the top two of the top teams to come in and present their results. And then I will speak to you again in a few minutes. Thank you so much.
Hi, everyone. My name is Rohit, and together with Shraddha, we have taken part in the food recognition challenge, round 3 of the food recognition challenge. Both of us are fourth years at SSN College of Engineering, Anna University, which is in the south of India in Chennai. And we'd like to talk about our solution for round 3 of the food recognition challenge today. So we'll be going over some topics starting from the problem statement. We'll describe the data set a bit. We'll talk about the data pre-processing that we did, the pre-trained weights that we used, the augmentations, the training schedule, the analysis that we did with the initial results, what we did to improve those results, which was label smooth cross entropy loss, test time augmentations, model ensembling, and the final results. So moving on, the problem statement was basically at its core, the food recognition challenge is an instant segmentation challenge where we have to look at a picture of food on a plate and try to predict exactly what food is present on the plate and where it is present on that plate. So this challenge specifically took data from the MyFood app. MyFood Repo app, where numerous volunteers across Switzerland took part, and they annotated the food that they were eating. And this was manual. This annotations happened either manually or were verified after they took place automatically. So the food recognition challenge itself has been a challenge that has been happening across rounds, in the sense that this is an evolving data set, and with every iteration, with every round, there have been new classes and new and more amount of data has been added for each round. So in round 1, we had 40 classes. In round 2, we had 61 classes. And in round 3, we had 273 classes. And this was the data that we used to train. So now coming to the data pre-processing part, The most important data pre-processing step that we used was to correct the bounding boxes in the data set to fit the mask correctly. And what we mean by this is that on initial data analysis, while going through the images, we noticed that the bounding boxes were quite often not fitting exactly where the mask is where they're supposed to be. That is, they should be around the mask. So if you look at the left-hand side picture, you can see that the bounding box is not even remotely close to the mask. I mean, there is some overlap, but that's not the bounding box that we need for that picture or for that mask. And the thing over here is that we noticed that in most of these annotations, the height and width had been exchanged or the x and y coordinates had been exchanged. So what we did was to not take a guess about what was actually exchanged. We just decided to recreate the bounding box from the mask itself. And on the right hand side, you can see the results of that, which is when we create the bounding box from the mask itself. So yeah, moving on to pre-trained weights. So initially in round one, when we took part, we basically used the detection framework, which is by OpenMM Lab, and we used the COCO weights for the HTC ResNext 101 with DCN. So HTC, by the way, is Hybrid Task Cascade, and it was fitted with the ResNext 101 backbone, and we added deformable convolutional neural networks as well. Deformable convolutional networks, my bad. And so in the pre-trained weights, we used COCO for round one. And when round two eventually came about, we decided to use the round one weights that gave us the score of 57.573 MAP. And we decided to use those for the model that was created in round two. And similarly, for round three, we used the model that was created in round two as pre-trained weights for round three. So this actually, our hypothesis was that this would help the model converge faster and basically, transfer some learnings from the previous round data into the current rounds. Moving on, coming to the data augmentations, we've used the very famous and popular library called Albumentations. And we have some pretty standard augmentations that we use. We use shift scale rotate, random rotate, random brightness contrast, and coarse dropout. And the probability you can see from the table that is shown to you. One of the other things that we did was to add either of blur, motion blur, Gaussian noise, or image compression. And most of the parameters that you see over here were taken after visualizing some outputs and seeing what they actually did to the images. So Shraddha will now talk to you about the training schedule and the models that we made.
Thank you, Rohit. So the training schedule that we use is, as you can see on the slide, so we use the SGD optimizer with a learning rate of 0.0025. And we took a linear step for the learning rate, decreasing it by dividing it by 0.1 at steps 18 and 22, with a total number of epochs being 24. And other thing that we wanted to accommodate was the fact that the training data set had multiple image sizes. So we wanted to use multi-scale training. And we did this within the limits of 1600 cross 400 and 1600 cross 1400. All of the experiments that we conducted were on a single V100 GPU. We wanted to analyze the results that we got. So the TightCV library breaks down object detection loss into its components: class, location, class plus location, duplicate, background, and mist. So as you can see, the TightCV results for the model that we trained is given in this slide. And by far, the greatest source of error was the class loss. So we wanted to hypothesize why this could be happening. After inspecting the data set, we noticed that there were some labels that were really closely related. For example, there were 20 different types of bread, like bread white, bread whole wheat, and so on. And also different types of water, like water, water mineral, water with lemon juice. These classes are difficult for even humans to tell apart. So it is quite likely that some of these have been mislabeled. So we decided to adopt a label smooth cross entropy loss to combat this. So label smoothing is a regularization technique that basically introduces noise for labels. It accounts for the fact that data sets have some mistakes in them. So we retrained our entire model using label smooth cross entropy loss on the entire set. By this we mean including the train set and the validation set, and we use the test set to validate. And this loss was only applied for the classification loss, and it led to an improvement of our score from 0.546 precision to 0.551 precision. The other thing that we tried was using test time augmentations that was already inbuilt in detection. So we used flip is equal to true and an image scale of 1080, 720. But this test time augmentation did not really give us any improvement in precision. And both using test time augmentation and without using test time augmentation, we got a precision of 0.551. We would have liked to try multiple image scales, but these do not evaluate in the time constraint of 2000 seconds per 1,000 images. So before moving on to cross entropy, label smoothing cross entropy loss, we did try a model ensembling technique using the validation set. So in this technique, we ensembled two different epochs of the same model. The way we did this was we ran two models, and each model would predict on a certain set of classes. And we decided this using class-wise MAP, assigning the model which has the higher MAP on a particular class to predict on that class. So since this particular approach involved running two models, we could not adopt test time augmentation into this approach, but it was giving us comparable results to the single approach model that did use TTA. So while ensembling the models of epoch 11 and epoch 15 without TTA, we got an average precision of 0.546 and an average recall of 0.868. And with just using epoch 15 with flip is equal to true, that is TTA, we got an average precision of 0.545 and an average recall of 0.869. So the final results was done using a single model with, or I guess without test time augmentation, using a label smoothing cross entropy loss. This model was, of course, the HTC model with the ResNext backbone and DCN. If you guys have any questions, feel free to reach out to us on the email IDs that you see on your screen, or contact us via LinkedIn. The challenge has always been very exciting and challenging, and we're looking forward to the new rounds of the competition.
Hello, my name is Eric Scuchamara, and I work on the Digital Nutrition and Health team at Nestle Research, and this is my solution to the food recognition challenge. The first and most important thing I did was fix some issues with the training data. Here we see some examples of training images where the bounding box does not match the mask. In most cases, they seem to have been rotated away from each other. I recreated all of the bounding boxes for the training and validation sets based on the masks. These are some examples of other issues with the training data. In this image, the cheese is not annotated. Here we have three different ways of annotating carrots. Here they are annotated as carrots, here as peas and carrots, and here as mixed vegetables. Mixed vegetables was my favorite category, more on that later. This image has multiple segments in a single annotation. The model tends to predict these as separate instances rather than as a single instance. And here we have three different ways that water is annotated. In this one, it is just the top of the glass, which bizarrely does not contain any water. Here it is the entire glass, and here it is just the visible part of the water. Many of these issues appear to be artifacts of the original hand annotation, which we can distinguish from the machine annotation by the fact that the mask edges are straight, jagged lines rather than smooth lines. These inconsistencies make the already difficult classification task even more difficult for the model to learn. The dataset has 273 classes, including 20 types of bread, 12 types of tea, 11 types of cheese, and 4 types of water. Many of these categories are very difficult even for a human to tell apart, and we will see that the classification was the major source of error. Like all of the other top scorers, I used detection, which was developed by the Multimedia Laboratory at the Chinese University of Hong Kong. It is very powerful and flexible with a large model zoo including pre-trained weights. It is also well supported and documented and easy to configure through the Python config files. Most object detection models include a region proposal network, which takes the feature maps output by the backbone and predicts the probability that a given region has an object in it and outputs a proposed bounding box and class. The proposals are used to extract the ROIs from the feature maps, and those ROIs are fed into the next stages. With object detection, typically the objects and images are not all the same size. Feature pyramid networks provide a way to address this. The bottom-up pathway is essentially the backbone where the feature maps are reduced in size as we go through each pooling layer. When we are making predictions, we use the top-down pathway. We start with the final feature maps and we make our predictions on that. Then we upscale that feature map by 2 times and add in the corresponding feature map from the backbone, merge them together, and use that to make our predictions. This allows us to make use of both the fine and coarse features of the images to detect objects at different scales. This is mask-RCNN, which was one of the first successful models for instance segmentation. It uses a backbone to extract the feature maps, feeds these into an RPN. The ROIs are extracted from the feature maps and fed into 2 separate branches, one of which produces the masks and another produces the classes and the bounding boxes. We note that the 2 branches run in parallel and do not share any information. Cascade RCNN improves on mask RCNN in that it has multiple detection branches which share information with each other. My best performing model was Hybrid Task Cascade, which achieved the best performance on the MS COCO benchmark in 2019. Hybrid Task Cascade leverages the relationship between the detection and segmentation tasks, interweaving the branches into a multi-stage joint process where information is shared between all branches and all tasks. The IOU threshold is gradually increased through each stage, iteratively improving the predictions. It also includes a fully convolutional branch to provide spatial context. For hyperparameters, I used the largest batch size that could be handled by the single GPU I was training on, which ranged from 2 to 6 depending on the model. This is produced by Tide, which breaks down the sources of error for object detection, and we can see that the classification loss is a major source of error. In order to attempt to compensate for this, I increased the weight on the classifier loss from a default of 1 to anywhere between 1.5 and 3.5. I got the best results between 1.5 and 2.5. However, increasing this weight only resulted in marginal improvements in accuracy. I evaluated learning rates starting between 0.002 and 0.02. The default learning rate decay is decay by 0.1 on epochs 16 and 19. I changed this to a more gradual but more frequent learning rate decay of 0.5 every roughly 8 epochs. One very important factor was the test config. Many of the correct predictions had very low scores and many of the incorrect predictions had very high scores. So I used a relatively low score threshold of 0.001, which had a big impact on the results. The maximum detections per image was also very important. In the training data, no image has more than 10 annotations. The default value is 100 per image, but I found no improvements in precision above 30, although that did improve recall. There's also a significant trade-off between this value and the inference time, and there is a time limit on evaluation, so I kept this to between 10 and 20 per model when I'm ensembling multiple models and 20 and 30 for a single model. The training data set includes a wide range of image sizes from 183 by 183 to over 4000 by 4000. The mean size was 645 by 645 and the median was 480 by 480, with 50% of the images between 480 by 480 and 852 by 852 and 80% between 400 by 400 and 973 by 973. Rather than picking a single size and resizing all images to it, I use multi-scale training where each batch is resized to a size randomly picked between lower and upper limits. My lower limit was 480 by 480 and the upper limit was 960 by 960. Some of the more memory-intensive models could not handle an upper limit of 960 by 960. For those, I used 800 by 800. The first place team, Rohit and Sharada, who unfortunately can't be here today, use an even larger upper limit of 1600 by 1400. However, using images of this size has a considerable expense in memory and training time. Data augmentation was critical to avoid overfitting to the training data. I used different augmentations with different parameters and probabilities for different experiments. So what you see here is kind of an overview of what I tended to use, though not exactly correct. I ended up decreasing the color-related augmentations such as RGB shift, as I thought it might be causing difficulty with the classification between similar categories such as the variations on T, and I ended up removing the channel shuffle for the same reason. The one of column here indicates that one of these augmentations is randomly selected for each batch, and I tended to increase the augmentation, specifically the rotation, up to a maximum of about 35 towards the end of training. All of my models were trained on a single NVIDIA Tesla V100 GPU. I would train the model evaluating every n epochs, where n was 5 at first and decreased to 2 after 20 epochs. When the validation score stopped improving, I would either increase the augmentations and resume training from the previous best epoch, or abandon the experiment and move on. I found test time augmentation very helpful. Each image was evaluated at 2 horizontal flips in 3 sizes, where those sizes are the lower and upper end of the training limits and the midpoint between the two. I evaluated a wide range of models, but the Cascade models were the ones which performed the best. The ones in red here are the ones which performed well enough to be moved on to the next stage, which was consideration as members of the ensemble. When we use TTA, each image is evaluated 6 times, and MM detection does not perform any merging of the results, which results in a large number of redundant detections, lowering the MAP. Casado Garcia and Haras propose a method for ensembling multiple detection models by grouping the predictions by class in IOU greater than 0.5. They then use one of 3 methods to determine which groups to keep and apply NMS to collapse each group to a single prediction. I found that the models often made correct predictions, very low confidence, so got the best results by keeping all of the predictions made by all of the models with the affirmative method. We'll also note that this method operates on the bounding boxes while we're interested in the masks. I attempted to do the grouping on the masks, however, converting RLE to binary masks was far too memory and time intensive to be practicable within the evaluation time limits. After having corrected the bounding boxes in the training data set to match the masks, the bounding boxes output by the model match the mask closely enough to be usable as a proxy. This is an example of merging the outputs from a single model. Note that the cheese is not annotated in this image. However, it happens to be the prediction with the highest confidence score. We have cheese duplicated and the jam duplicated, and after merging the results, those duplicates have been removed. After having established that merging the results improved the performance of a single model, I was able to use it to ensemble multiple models. I made a few changes to the method originally proposed. Instead of using the score for the NMS, I add an additional weight which multiplies the score by the area of the bounding box. This is an example of why I did that. We see here that the salami is annotated as a single instance. However, the model could be predicting it as multiple instances. By taking the area of the bounding box into consideration, we can favor the larger predictions over the smaller ones. After applying NMS to collapse each group to a single prediction, I assign that group the maximum confidence score from the group to counteract the effect of the weighting. In an attempt to reduce false positives, I had tried to only keep detections made by multiple models. However, this ended up reducing the score. However, reducing the confidence of detections only made by one model ended up raising the score, so I did that, but only when combining the results of multiple models, not when merging the results of a single model. The code I wrote for this merging operated on the JSON outputs of the models, so each model had its outputs merged and written to JSON, and then I ran the code again to merge the outputs of the 3 models to the final outputs. This is an example of merging the results for 3 models. We note here that the bread is annotated as a single instance with 2 non-continuous segments, whereas the model is predicting it as separate instances. After merging the results, we see that the 3 correct detections made by the model are at the top of the list sorted by score, and that, for example, the carrots have had their scores decreased because they were not made by multiple models. We can also see here that the infamous mixed vegetables is not being predicted as mixed vegetables, but as being predicted as the individual vegetables, carrot, radish, tomato, onion. My final ensemble consisted of 3 models, Cascade Mask RCNN with a ResNet 101 backbone. While this model did not perform very well on its own, it apparently added something of value to the ensemble. The other 2 models were Hybrid Task Cascade with a ResNet 50 backbone and Hybrid Task Cascade with a ResNext 101 backbone. Note that the validation scores tended to be about 0.1 lower than on the test set, which I assume is because the test set is higher quality. I was able to get slightly better results by using 4 model ensembles, however this was not possible within the evaluation time limit. My final score for round 3 was 0.520, although I have been able to improve that to 0.555 in round 4 by addressing some of the previously mentioned data issues. The models performed very well on the segmentation and detection tasks and output masks and bounding boxes with no problems. The difficulty was with the classification. On the validation results, if I just remove the incorrect classes, I can increase the MAP by 0.2 without changing anything else. It was also interesting that the confidence scores were largely useless and irrelevant. Often the incorrect detections had a very high confidence score while the correct ones had a very low score. This is a very difficult and challenging problem, and I enjoyed working on it a lot. This is probably the only data set I've been able to find with quality annotations of real pictures of food taken by real people. Thank you to everyone involved in putting it together, and thank you for your time.
Thank you so much, Eric, Rohit, and Shraddha. Before we conclude the talk, we wanted to mention that this whole benchmark and the results that we obtained throughout the whole last year, it has been a fun journey, but it would not have been possible without the generous support of the C-Ray Foundation, our partners at EPFL, and particularly the team behind the My Food Repo project and the Food and You project. That said, there's also the whole AIcrowd community to thank for, who came together in large numbers and submitted 2.5 terabytes of code and model to help us make progress on this problem. That said, this is not the end, this is just the beginning. We hope to continue running this benchmark, and we hope to help push the state of art in the use of AI for understanding food composition in images. Thank you so much.
Thank you very much for the nice presentation. And actually, there is one question in the question and answer tab. Is there a cultural or geographic bias in the My Food Repo Pictures database? For example, most of them representing Western food, and how were the 273 classes decided?
Sorry, I was muted. That's a great question, and there is indeed a very strong bias. All the images in the dataset are collected using the Food and You project from cohorts of Swiss volunteers who have contributed these images. So a majority of these images are from people from all over Switzerland who are contributing images of food that they have. And for the second question of how the food classes are selected, so this is the food classes were principally selected at EPFL by the team behind the My Food Repo and the Food and You project, where it was from an ontology of food classes, which was published by the Swiss government, if I'm correct. And then as the images started coming in, these images were mapped by annotators, expert annotators, to these individual classes. And then we worked on the data that was collected through the process.
Okay, thank you for the answer. There are two more questions. Is there an app where we can make pictures, get a result, and can say how good the result was, or a prototype app for food recognition?
Right now, there is an app which is, again, the whole idea behind the Food and You project is you take pictures of the food that you consume every single day. And the project tries to kind of do that with the minimal barrier to entry or minimal effort itself. They do not expect you to kind of take a picture, write a lot of notes of what do you want to eat. So they want you to take a picture, send it to them, and it's their headache now to ensure that these are annotated. So for now, to the best of my knowledge, you have to be a part of the cohort. But I think the team both at AIcrowd, EPFL, and Food and You are working very hard to ensure that we can open the floodgates and let anyone use the app.
Okay, thank you. This was a question from Frank Quedenfeld. And there is one more question from Elena Mikosi. How can you classify highly processed foods?
For highly processed food, I think that's an interesting question. We are not dealing with that problem per se in context of this particular challenge, because we wanted to look at daily cooked food and stuff. But the data set that is collected through Food and You and also my food repo also includes a lot of data about processed food items. There, the question is, if you have a food item which is highly processed, in many of the cases because of regulations at different places, you also have the barcode information and the nutritional information. Then the question is, do you trust that nutritional information, or in general, what is the variance in that nutritional information? So given that you can map it to one cluster of data, and then you can invest separate resources in getting a much better understanding of the nutritional composition or the variance in that cluster of data, it's easy. If I understood the question correctly.
Okay, thank you very much for the answer. And maybe I don't see any other question in the question and answer tab, but there is one question by me. Actually, I'm wondering about, you already explained that for the classes you use some food ontology, which is actually developed by the Swiss government. But on one of the presentation, I think the second one, I'm not sure if this is in your database, but actually in your data set, there was some mixed vegetables, and then it was like vegetable mixed with carrots and so on. If the classes are disjoint, are they normalized to some semantic resource? For example, if some text normalization is performed, or it can be like several classes can overlap between?
Okay, that's a great question. Actually, it touches upon a very important point of it. So actually, the whole project was started when I was still a PhD student at EPFL. So we went through the messy process of trying to figure out how to kind of map these classes and the relationship between them. Interestingly, right now, when we are training the models, we are not even using that ontology information per se, but that actually causes some issue, and we are working hard on figuring out how to, decouple these classes or merge some classes. But for now, many of the classes, there would be overlaps. In fact, annotators could be confused, and probably a little bit more work needs to go into figuring out how do we properly disjoint, ensure all the classes are disjoint, or we have a better understanding of the relationship. But if we went into the effort in the beginning of trying to figure out the perfect grouping of classes and their ontology in the beginning, we would have never been able to kind of collect this much amount of data, because again, the whole process would have been taken a lot longer and a lot more confusing. Now, given that, using this broad ontology that we kind of received, from some reports in the Swiss government, and then we worked on top of it by adapting it a little bit along with the annotators. In the process, by looking at the annotations that we have received and how many annotations occur with each other and the predictions made by the model, we are in a much better position to make decisions which are informed by the actual data from actual users to better align these ontologies, better align these classes and their relationship. But this is a major focus internally right now on figuring out what should be the optimal minimum number of classes that are needed to efficiently represent all these images, and what is the relationship between them.
Thank you very much for the nice explanation. And I know how difficult it is to do something like this, and even collecting the data set, like it is a really time consuming task and not like deciding for which classes to be involved. Thank you again.